let us know what are actually the advantages of the state space analysis compared to the conventional method. Conventional method means whatever we have seen so far. So in the conventional methods, like RH stability criteria, root locus, Bode plot, Nyquist plot, these are used in the used for the stability analysis of linear time invariant control systems. Okay, and these methods are modeled, or this modeling of the control system happened based on the transfer function approach, either electrical systems or mechanical systems, whatever. All we have calculated the transfer function by using the differential equations, right? And the differential equations, with the help of Laplace transform, we have converted into transfer function, right? This is in the conventional approach. We have seen this, and because these conventional methods are using the transfer function format, whatever the problems are exist through this transfer function approach, those are applicable to all these methods. Like in the while deriving the transfer function, nowhere we have considered the initial conditions, right? Yeah, all initial conditions we assume zero. That means when we have d by dt of f of t, we put simply it is f of s. So yes into f of s. But actually the derivative of f of t is equal to s into f of s minus f of 0. Right, Pallavi? Understood this?
Yes, sir.
The initial conditions are also there in the formula, actual formula, but we are not considering anywhere this minus f naught. So all these initial conditions are we neglected in the conventional approaches. So if we consider the transfer function derivation is difficult. Okay, so a new approach to this conventional methods is evolved. So that is nothing but the state space analysis. And this conventional methods also is useful for linear time invariant control systems. But whenever the system is non-linear, these conventional methods are very complex. So not we can't use these methods. Little bit advanced methods we need to use to study the non-linear time invariant systems. And also these conventional methods we have seen for single input, single output system. So we have given at this point u of t, and at the end we got y of t, right? So this kind of single input, single output systems we implemented so far. But the problem is whenever you try to implement the multiple with the multiple inputs to get the multiple outputs, the system design is a little bit complex in the using conventional methods. But whenever you have multiple input and multiple output, the system analysis is easy in the state space domain. Therefore, all the advantages are there with the state space analysis. But therefore, if you take the limitations of convolution, the conventional methods, the first limitation is initial conditions are neglected. And next is it applicable only for linear time invariant systems. And it is not convenient to design multiple input, multiple output system. And these are the classical methods we use to study the stability or to calculate the errors, something, and optimal solutions for the conventional approaches, which are not suitable to find out or study the analysis of MIMO systems as well as nonlinear time invariant systems. And all these systems are having some like a trial and error approaches. Um, just try this and change this value and get to what will happen to the stability and what will happen to the pole locations and that. This all this kind of approaches are like time invariant error and approaches. Okay, but if you compare to the advantages, we compare to the advantage of state space analysis, all these drawbacks are come under advantages of state space. We can count the initial conditions. So with the initial conditions, we can find out the response or we can analyze the system. And second advantage is it is also used to design the MIMO systems. We can analyze the MIMO systems also. It's very analysis is very easy. And the next advantage is it is also used for linear systems as well as MIMO systems. Sorry, non-linear systems. Linear and non-linear, whatever the system is, you can analyze the system. And time varying and time invariant systems. Anywhere, any type of system is easily can be analyzed using state space analysis. And next advantage is it gives the information about internal behavior as well as the input output behavior of the system. So internal behavior and input output relation through transfer function you can get internal behavior in the sense at each node the what is the state condition. So that also can be determined using the state space analysis. Basically, when you have a circuit, we in the transfer function domain, we calculate what is the output when you do this kind of input. That is output by input will give directly the transfer function. In between at each node or at any takeoff point or summing point, what is happening? What is the state of the system? That cannot be determined. But here in state space domain, whatever the state at any node you can easily analyze it because state space representation involves the state variables. So the state variables tells what is happening in the middle or internal behavior of the system. These are the limitations and advantages. Please note down this may come for 2 marks, advantages and limitations. Now next is we'll see the basic terminology. So basically all the definitions, it may come as one lengthy question, 8 marks question. Otherwise, they'll ask for two marks questions. What define the state with an example. Like that way, each and every definition, they may ask for 2 marks question. So let me start with the state. State, see what state in the sense, any set of variables, if defining if x of 1, x of 2, x of 3, say these three are the variables, are the features of a system. With these three features, if we can define, if we can describe the system behavior, overall behavior, then these at a given time, these features is called a state. So for example, see, you want to estimate your financial status at this time, at this moment. Then how to define that? You need to check your bank account. Okay. And what is the status of your education? And what about your assessments? Everything. If you want to check about your assets, everything you will come under account. So after calculating all this, then you can estimate where I am at this moment in with respect to my financial status. So that state at this particular time, at a particular time, okay, at this state of you at this particular moment depends on so many factors at this moment only. Okay, then this with these features at this moment totally describes you at this moment. This is called state, your state, right? Understand what is meant by state? Pallavi, are you there?
Yes, sir.
So, if you take any system, suppose you have an electrical circuit. So, electrical circuit, if you want to calculate something, what is the value, what is the voltage across a component? If you want to know what is the status of this, what is the status of this circuit, then how can you define the status of this circuit? You need to know what is the voltage at this point, what is the current flowing through this, okay, and what is the current flowing through this. So with this information, you can understand what is the status of this circuit. Okay, so some features, based on some features of a system, we can define the state of that system at that particular moment, at that particular time. Okay, that is the state. So state includes the state variables. What are the state variables? How to take the state variables? State variables, you can select any number of state variables, any variables which can describe the system behavior. Suppose if I feel that I will take the voltage at this node, that helps to describe the system behavior, or the current passing through the system, or current voltage across through these terminals. If I feel this will describe the system of behavior of this circuit, I will take it as a variable that is called the state variable. And state includes all the state variables. Any number of state variables you can take it, but optimal number will give you the state variables will be included in the state. State variables, all state variables may no need to be included in the state. Okay, sometimes the voltage at this point, voltage across this capacitor. See, this V1 is equal to VC only. Why need to specify V1 and VC both? Not required, because these two voltages are same only. So instead of taking these two, I will feel separately. If I look V1, I say it is a state variable, and VC also state variable. Okay, but when I consolidate these two, I feel one is sufficient. So that is the optimal variable. Only one variable enough. That variable only will be included in the state. Duplicates we should not take. On either V1 or VC we will take in the state. Okay, but if you talk about separately, V1 I will say it is a state variable, VC is a state variable. Okay, and similarly, any number of state variables you can take from the circuit, but we should optimize these state variables. If any variable is giving the same information which is already describing by other state variables, that respective state variable can be neglected. So one variable will give some unique information about the system. And next is the state vector. State variables are defined as x1 of t, x2 of t. This is the way we can describe. For example, give a circuit and take this is the V1 voltage and the current passing through this resistor, say I of t, like that we can mention it. All these are the state variables. And state vector. How to define the state vector? It is an n-dimensional vector where state vector is suppose you have two state variables, x1 of t and x2 of t. Suppose in a state, x of t, you have two state variables, x1 of t and x2 of t. So the state always represented in the column matrix. Okay. So if this is the state and x1, x2 both are the state variables, this is the state and these two are the state variables. State variables. So if we have two state variables, you can draw a graph versus x1 of t and x2 of t. Okay. Then this graph will give you the relation between two state variables. That means at a particular time t naught, what is the value of x1 of t? Suppose they say this is the x of x1 of t naught. At t time t is equal to t naught, x1 of t value is x1 of t naught. Say, and at the same time we will be having some x2 value also. So say that is x2 of t naught. So then combinedly we can place one value at this intersection point. So this plane is called state vector from this origin. What is the vector to this point? State vector. Sometimes we will be having a t1 to t2. So this is the t1. This is x of t1, x2 of t1. From this point to this point, it is the state vector. Okay. That way we can draw the state vector between the state variables. So it is an n-dimensional state space. So it is an n-dimensional vector whose components are n state variables. If it is having three state variables, then you should draw the vector in three-dimensional field. Okay, 3D. And what is the state space? Next one is the state space. State space is nothing but it is previously shown is a space whose coordinates are the x1 of t, x2 of c, and so on. That means state variables. This space, this space is the this space is the state space. State space. And this is the state vector. Okay. And state trajectory is also there. State trajectory is given by state trajectory state trajectory. Suppose you have two state variables x1 of t and x2 of t. So it's suppose x1 of t, you say this is the value at t is equal to t1, and this is the point state vector. And suppose say you have one more point at t is equal to t2. This is t is equal to t1, and at t is equal to t2, say suppose the point is here. Point is here. So this is t2. Then the joint between this is called state trajectory. So this is the point from initial value to t1 time, and this is the point from initial value to the T2 tag. And between these two, the connection between these two, the vector between these two values is called the state trajectory. Okay. Pallavi, understood?
Yes, sir.
Yeah. Now, these are the definitions over with a simple diagram or example. We should explain each term. Basically, you will get for 2 marks these questions. Next question is the state model. What is meant by state model and how to generate the state model from the diagram? Suppose you say you take this is the MIMO system, multiple input, multiple output system. Here m inputs are there. Suppose say U1, U2, U3 and so on Um. M inputs are there to the system. Okay. And for this system, you will get p number of output variables by 1, by 2 and so on by p. Okay. See, in order to get these y variables, intermediate behavior of the system is described by the state variables. And here you say n number of state variables are there for this given control system. That those are x1, x2, and so on x. Now, based on these inputs variables and the state variables, we can describe what is the output. That means how the system will behave and what kind of output you will get. Therefore, you can relate this y in terms of x and u, correct? So for this relation is nothing but state modeling. So output behavior is determined in state, yes, in terms of input and state variables. So input is applied to the system, and the state variable changes based on the system behavior. So completely the state system behavior is depending on the state variables. Indirectly, we are representing the behavior of the system in terms of variables x1 to xn. So to get this relation, let us mention all the variables in matrix format. So first, input vector u of t is mentioned in the column matrix u1 of t, u2 of t, and so on, um of t. Okay, and say this is the input vector of the dimension m by 1 because m rows are there and single column. Okay, and next state matrix. State matrix we represent with the state variables. Here n number of state variables are there. Again, you represent in a column matrix. So the dimension of this matrix is n by 1. N state variables are there in a single column. And last matrix, output matrix. So this is represented as p variable, p number of variables, y1 to yp. Therefore, its size, matrix size is p by 1. Okay. Whenever there is a single column, it is called a vector. Okay. So that's why this output matrix is also called output vector because it is having single column only. Okay. Now everything is represented in the vector format. Now we will define this y of t in terms of x and u. So you assume this y1 is related to x1 and u linearly. Therefore, these coefficients, you can assume any coefficient, some coefficient. Here I assume C11 into x1 plus C12 into x2 and so on plus C1n into xn. So this is linearly related with the x1, the state variables. Plus, similar way, this is also linearly related with the u variables, I mean input variables, d11 u1 plus d12 u2 and so on, d1m um. That is only for y1 variable. Similar way, we need to take the relation for y2 in terms of x1 to xn and u1 to um and so on. In the last variable, yp is related to x1 to xn and u1 to um linearly. Now, these total equations, P number of equations we got. These P equations are represented in the matrix format like this. So, we have P number of Y variables. So, Y1 to YP, a column matrix. Okay. And this equation is represented as Cx1, x2, x3, and so on, xn are common for all the equations. Therefore, we take it as a column matrix like this. And remaining coefficients are changing it in each equation as well as for each state variable. Therefore, this is represented as a square matrix C11, C12, and so on, C1n, and C21, C22, and so on, C2n, and so on. So this is a square matrix of the size P rows and n columns. Since it is a state matrix is n by 1 size, whenever you multiply this, the multiplication rule of the matrices is satisfied. Therefore, the resultant matrix will get P into P by 1. So that is the output size. So whenever you multiply these two matrices, again you will get this kind of equations. Okay, this is with the state variables. Similar way, we need to add this matrix result with the U coefficients. Therefore, again for the U variables also, this part, you write the equation. It is D. Okay, D11, D12, and so on, D1m. Okay, and so on. So this is again a square matrix of size P by M, and we have M number of input variables. Therefore, again here the matrix multiplication condition is satisfied. Therefore, we will get the resultant matrix size of P by 1. So P by 1 matrix, P by 1 matrix, both are added, and the result is nothing but the output matrix. Okay. This is the relation between the output variable and input and state variables. And also here, state variables are also selected, and we have defined in such a way that it's a derivative, first order derivatives exist. So whatever you select the state variables, that you should not select it is it is not derivative. It is not differentiable. Should be differentiable only. So if it is differentiable, all the state variables, then the relation between the first order derivative of the states with the states itself, state variables, and the input variables is like this. Again, this relation is a linear relation. So the first order derivative of x1 variable is related to all the state variables linearly, like this, and all the input variables like this. Similar way, the first order derivative of x2 variable also depends on all the state variables and the input variables, and so on. All the first order derivatives of the state variables are defined. And when you write these equations, here n number of equations are. If you write these n equations in matrix format, we get this x1 dot, x2 dot, and so on, xn dot. This is of n by 1 matrix, n by 1 matrix, and this is n by n matrix, because here a11, a12, and so on, a1n. So number of columns also n, and number of rows also n, a11, a21, and so on, a1, an1. So n by n matrix we got, and here the state variables are x1, x2, and so on, xn. When you multiply this matrix with this, again you get these equations, this part of equations will get, and plus this is added with this state input variable with the coefficients. So how to write this in the matrix? b11, b12, and so on, b1n, n columns and n rows, totally again here it is m, not n. So it is n by m matrix, and because this is having m number of input variables, so its size is m by 1. Whenever these two are multiplied, the resultant will be n by 1 matrix. So here also this n by n into n by 1 will give finally n by 1 matrix. That is the state matrix. So this total equation is simply written as x dot of t is equal to a into x of t plus b into u of t, where x of t is equal to this state vector and u of t is the input vector. A is this A coefficient matrix, B is this B coefficient matrix. So it's a simple way of representation of this big matrix equation. And this equation is denoted as state equation. Okay. And we already know the dimensions of each matrix. So this is the state equation. And in the previous equation, we got the matrix equation for y output is equal to some C matrix into x of t plus b into u of t. This is called the output equation because we got the expression for output y of t. So for m by mo system, we got what is the state equation and output equation. So the state equation and output equation combinedly we call it as state space representation of a given system. If we can represent this in this matrix formats, then that representation is called state space representation. That is equal to the state equation plus the output equation. Okay. Pallavi, understood?
Yes, sir.
Okay. And okay. Okay, time is up. We can continue this in the next class with the single input, single output system. Okay. And just let me take one more minute. Let me finish this MIMO system. It is simply a diagram. Sometimes they will ask to draw this MIMO system state diagram. So state diagram for MIMO system. It is nothing but state equation and output equation combinedly we represent in a diagram. That's it. So what is here? Input is u of t, we mentioned at the left side, and output is y of t, mentioned at the right side. And what is the x of t? X of t is a middle variable. So it represents the internal behavior of the system. So leave it at this moment. Then y of t is equal to what? C into x of t plus d into u of t. So it is just a summation of two inputs. One is c into x of t, another one is d into u of t. So how to get d into u of t? From the u is here. If you can multiply this with the d matrix, you will get d into u of t. And the second input is the c into x of t. How to get c into x of t? You don't have x of t, but you assume here some x of t is there. So that x of t, if you multiply with C matrix, then you will get C into x of t. So you got. So far you got till this point. Till this part you got it. The output equation. And continue the block diagram with the state equation. State equation is nothing but x dot of t is equal to a into x of t plus b u of t. You assume somewhere x of t, x dot of t is here, somewhere you assume. And this x dot of t is the sum of two terms. So make a summing point and with two inputs. One input is coming from x of t. So x of t already we defined here. You multiply this with A matrix and connect to the summing point. And the next input is b into u of t. So it comes from the u of t input. And multiply this with the B matrix and join to the summing point. Therefore, you get x dot of t. But here, after implementing this part, you have a gap between x dot of t and x of t. So how can you relate these two variables? Since x dot of t is equal to d by dt of x of t, how can you get x of t? X dot of t is equal to d by dt of x of t. Therefore, if you want x of t, you can write it as integral of x dot of t dt. Then you can get x of t. So the relation is x dot of t is integrated in time to get this x of t. Okay. Now the diagram is completed. This is called state diagram.